Okay, all right. So welcome to the lecture for June 29th, as first lecture of week 3. Just to let you know, I'll get around to grading your exams soon, but I sort of had a lot going on this weekend, so I wasn't able to get around to it yet. Like always, let's start off with the warm-ups here. So give those a shot, and then I will work them through. Okay. Hopefully you have paused the video, given them a shot. Let's go over the answers. So for this first one, we'll rewrite it first as y double prime equals negative 3y prime. So if I sort of do a change of variables, though I'm not actually going to introduce a new variable here. So I'm just thinking of this as y prime equals negative 3y prime, which means we know that y prime is some constant c1 times e to the integral of negative 3 dt. So we get y prime equals c1 e to the negative 3t. Okay, so now we integrate both sides. So y is the integral of c1 e to the negative 3t dt, which means we get c1 over negative 3 e to the negative 3 dt plus some other constant c2. And to make our lives easier, we can absorb that negative 1/3 into the c1. So y equals c1 e to the negative 3t plus c2. That's our general solution, but we're told to solve an IVP. So we have y of 0 equals 2, which we see y of 0 equals c1 e to the 0 plus c2. So we just get that c1 plus c2 equals 2. We're also told that y prime of 0 equals 9. So y prime is negative 3 c1 e to the negative 3t plus c2. Or, sorry, plus 0, because derivative of a constant, right, is just 0. And so now y prime of 0, we have a negative 3c1 e to the 0 equals 9, and so negative 3c1 equals 9. Just dividing through, this tells us c1 equals negative 3. And now we can go back here, negative 3 plus c2 equals 2, so c2's got to equal 5. And now remember, we're not done, we just got to plug it all in. So y is c1, which is negative 3, e to the negative 3t, plus c2, which is 5. And that is our answer. Okay, so hopefully that was pretty straightforward. Let's go on to a slightly less straightforward problem, though I did give you guys a hint, sort of reminding you how we can solve these if we know one solution. So we want to do a change of variables, and sort of our goal is we want you to have a constant solution. So after the change of variables, whatever our new variable is, like if we plug in 1, that should be a solution to the equation, because that means we're not going to have like a y term and we can sort of do the same thing. Okay, so well, what are we going to do? Well, we just set u equal to 1 over t times y, right? Because if t is a solution to this, then in terms of u, right, we'll just get 1, and this should correspond to a solution in our new equation. Okay, So if u is 1 over t times y, right, then y equals t times u, which gives us that y prime is t to the u prime plus u, and y double prime is t to the u double prime plus u prime, or t u double prime plus 2u prime. Okay. So now we'll change our variable to be in terms of u. So y double prime is tu double prime plus 2u prime plus 6 over t y prime tu prime plus u minus 6 over t squared y, which is just tu. And now let's simplify, and we did it right. We should lose all the u terms. So we have tu double prime plus 2u prime plus 6u prime plus 6 over t times u minus 6 over t times u. All right, so we did it right. Those both cancel. And we are left with tu double prime plus 8u prime equals 0. Okay, so let's go ahead and solve this now for u. So u double prime equals negative 8 over t u prime. So again, just like above, treating this u prime as its separate variable, we get u prime is c1 e to the integral of negative 8 over t dt, which simplifies to c1 1 over t to the 8th power. Okay, so that is our u prime. So our u is now the integral of c1 over t to the 8th. So that tells us that u is c1 times t to the negative 8. So that's going to be, you add 1, gives us negative 7 divided by it. So negative, or 1 over negative 7 t to the 7th, plus now some other constant, c2. And we can go ahead and absorb that. So u equals c1 over t to the 7th plus c2. Okay, almost done. Just have to undo our substitution. So looking back, we recall that u was 1 over t times y. And so y is c1 over t to the 6th plus c2 times t. And this is our general solution, which is our answer. Okay. So moving on, let's get into today's topic. So we're going to be talking about fundamental sets of solutions at the end, but before we get into sort of identifying them, we're going to have to do a review of some matrix algebra. So just to learn a little bit of matrix algebra. Okay. So just to give you the definition. So given a homogeneous linear equation, so y double prime plus pt y prime plus qt y equals 0, a fundamental set of solutions which we're often going to abbreviate as FSS, is a pair of solutions so that the general solution to the above equation is y equals c1 times y1 plus c2 times y2. So we've solved a number of homogeneous equations, usually of special forms, but just to recap what we just did, right? Here, our fundamental set of solutions could be e to the negative 3t and 1. And here we could see that our fundamental set of solutions could be 1 over t to the 6th and t. So as we'll sort of see by the end of class today, every sort of equation of this form is going to have a fundamental set of solutions. And we're going to have a test to identify or verify that a given pair is a fundamental set of solutions. So this is going to make solving these equations a lot easier, because if we can just find two solutions that are sort of different enough, then we can be sure that we have everything. So how are we going to go about this? Well, as I mentioned, we're going to have to do some matrix algebra. Specifically, we're just going to look at the basics, 2x2 matrix algebra. Okay, so first of all, what is a matrix? We'll just do so it's a really nice way of sort of representing certain systems of equations. So way to represent specifically linear equations. So here's sort of the deal. If we have something like, let's say, 2x plus 3y equals 1, and negative x plus 4y equals 2, then we represent this sort of as follows. So I'll tell you how we represent it, and then I'll explain sort of why we represent it that way. So if we make sure that the variables are lined up in sort of rows and columns, we just sort of steal, okay, that's a 2 there, that's a negative 1 there, that's a 3 there, that's a 4 there. The first column are the x coefficients, so we write an x here. The second column are the y coefficients, so we put a y there. And then we have our 1 and our 2. So all of these things are matrices. So this is a 2x2 matrix. And these are both 2x1 matrices. or often we just call them 2x1 vectors. So if we have a matrix, there's a couple rules that we have. So we can add two matrices. So and the way I do that, if I add two matrices, they have to have the same size. So they have to be the same shape, basically. I can't add A, B, C, D, and let's say I have V, which is UV. I cannot add A to V. But I can add A and B, and I do that by just adding up this entries. So the first entry is going to be A plus P. The second entry is going to be B plus Q. The entry down here in the bottom corner is C plus R. And the other corner is D plus S. Okay. Now, there's also a rule for multiplying matrices, and it's sort of pretty different. It is not just multiplying entry-wise. In fact, we can actually multiply things of different shapes. So here's how we do this. So A, B, C, D. So for the first matrix, we're going to sort of take this first row, and then we'll take like this first column. And what we do is we do, okay, the elements in this first row, A times the first element in this row times P. So A times P plus B times R. To get the second entry, right, I would do A, or the entry right here, I would do the same thing, except now I'm going to use the second column. So if you think of this as being the entry in the first row in the first column, I take the first row and the first column. For the second entry, I'm going to do first row, second column. So I'm going to have A times Q plus B times S. And then I would repeat that down here. So I'm in the second row in the first column. So I'm going to do CD times PR. So CP plus DR. And CD times QS. So I can also multiply A times V. And the key thing is that there's the same number of elements in each row in the first one that there are as many elements in the columns of the second one. So here it's a little bit simpler, but I take first row, first column. So I have A times U plus B times V. And then CD times UV, so CU plus DV. Okay. So a couple things to note. So pair of facts. So A plus B is the same thing as B plus A. However, A times B is not the same thing as B times A. It could be sometimes, but most of the time it's going to be different. So as an example, if I do 0, 1, 0, 0 times A, B, C, D, then I get here 0, A plus 1, C, 0, B plus 1, D, and then here 0, A plus 0, D, 0, B plus, oh wait, that should be C, and 0B plus 0D. So I'm going to get here, well that's 0, that's 0, that's 0, so I get C, D, 0, 0. If I switch the order now though, C0 plus D0 and C1 plus D0. Then I end up with instead the matrix 0A, 0C. And as we can see, these should not be the same, at least for, basically all choices for A, B, C, and D. Okay, there's two sort of special matrices. The first, which we just sort of represent as an I, is the identity matrix. And this is the matrix where there's a 1 on the diagonal and 0 is off the diagonal. The second one is the 0 matrix, and this is the entries with all 0. So we'll start with the properties of the 0 matrix. So if I have A and I add the 0 matrix to it, A here being the A, B, C, D, then, well, I'm adding A plus 0, B plus 0, C plus 0, D plus, I just get, no entries change. So really, A plus anything, or A plus the 0 matrix is just A. Similarly, A times the 0 matrix is the 0 matrix. So the 0 matrix really does sort of behave a lot like 0. Over here, the identity matrix behaves a lot like 1. So we'll see that if we do I times A, then we end up with 1 times 0, so 1A plus 0C, 1B plus 0D, 0A plus 1C, and 0b plus 1d. And so that just becomes A, that becomes B, that becomes C, and that becomes D. So the identity matrix times A is equal to A, and the same thing is true if you multiply the other way. Okay. So now here's sort of going back to just like equations. So if we have so we want to write the following system: 2x plus y equals 7, and 5x minus 3y equals negative 10 as a matrix equation. So we already sort of have, I already sort of told you how to do this up here. We just sort of make sure the variables are in the right rows, and we just sort of, treat this as a square, write down what the coefficients are, and then sort of similarly for everything else. But let's see why this works. So we have 2, 5. This is our x row here, right? This is a 1. So that's going to be a 1, and then we have a negative 3 times xy. And if we multiply this out, we get 2x plus 1y in the first entry. There's no second entry over here because this doesn't have another column. And here we have 5x minus 3y. So just simplifying once more, 2x plus y equals 5x minus 3y. And so up here we can see, oh, this is the same thing as there, and 5x minus, oh, we have that right here. So this equation, or this system of equations, we can write this, we want this to be equal to 7, because that's what we want this entry to be equal to, and negative 10. So yeah, we can just sort of confirm it. Our answer here would be 2, 1, 5, negative 3, xy equals 7, negative 10. All right, so to give you guys some practice, let's have you do a couple exercises. So 1302. B is going to be the matrix 4, negative 1, 1, 5. And V is going to be the matrix 7, negative 2. So just compute this. Get a little bit comfortable with, the matrix multiplication stuff. And then number 2, write 11x plus 4y equals 5. and 8x plus 3y equals negative 2 as a matrix equation. Then write 1, 2, 0, 1 times xy, or I'll change the variables, times a b equals 10, 8 as a system of equations. So convert it to something of this form. And then also solve the system for a and b. Okay. So give those a shot. And okay. So hopefully you've paused, given them a shot. Let's go over the answers. So first we'll compute b times a. So that is 4, negative 1, 1, 5 times negative 1, 3, 0, 2. So we have first row times first column, 4, negative 1, plus negative 1 times 0. Then we have first row, second column, so 4 times 3 plus negative 1 times 2. Second column, first row, not 5, but 1 times 0 plus 5 times 2. And 1 times 3 plus 5. Oh no, okay. Everything's right. Okay, I gotta change this. This is not right. It's 1, 5 times negative 1, 0. And so let's see, we have negative 4 plus 0 for the first entry. Here we have negative 1 plus 0. Here we have 12 minus 2, so that gives us 10. And here we have 3 plus 10, so that gives us 13. So that would be our final answer there. A plus B, pretty simple. A plus B, just do it entry-wise, 3, 0, 2 plus 4, negative 1, 1, 5. So that is negative 1 plus 4 is 3. 3, negative 1 is 2, 0, 1 is 1, and 2, 5 is 7. And lastly, we want to compute A times V. So A times V, that is negative 1, 3, 0, 2 times 7, negative 2. So we have negative 1 times 7 plus 3 times negative 2, and 0 times 7 plus 2 times negative 2. So we have negative 7 minus 6, so negative 13. And here we have 0 plus negative 4, so negative 4. So A times V, is negative 13, negative 4. Okay. So going down here, right, we have, this is just going to be 11, 4, 8, 3 times xy equals 5, negative 2. So that would be our answer for the first one. And if we write this so we do the multiplication, so we should have a plus 2b in the first one, and 0 times a plus b, so just b in the second one equals 10, 8. So if we convert that, we have a plus 2b equals 10, and b equals 8. And if we solve this, well, b is sort of already solved for us, but we should have a equals negative 6 and b equals 8 as our solutions there. Okay. So I'm sure you are all wondering why we are talking about matrices. This is so very, very, very different than everything we've been doing up to this point. Well, the reason is we could have probably skipped it and I could have just sort of told you some facts, but we're also going to need this towards the end of class, so that's one reason. We're going to be studying sort of matrices which represent differential equations, and having some of the matrix terminology is going to be really, really important there. Okay, but the second reason is this next part, so inverse matrices. And determinants. So an inverse matrix for A is a matrix which we call A inverse, so that A inverse times A is the identity matrix, which remember is this thing, and A inverse is also the identity matrix. The determinant of A, this is actually something that you should have seen before. It's possible it wasn't called that when you took Calc 3. But what we do is we do the product of the main diagonal, so A times D, minus B times C. So these two things are very closely related. So just a fact, which is why we're doing this. So A inverse exists precisely when the determinant of A is not 0. Moreover, we also have just a formula for A inverse. So A inverse is 1 over the determinant of A times, I guess I should say, okay, so if, again, just emphasizing, so we have A, B, C, D here. Here's how we get the inverse. So we divide out by the determinant. We swap A and D, and B and C we just make negative. So to use the formula for the determinant over here, AD minus BC, DA negative B negative C. Okay. So here's our formula for A inverse if A is A, B, C, D. And we can see here why the determinant needs to be 0 because we divide by it. So here's why this is useful. So given a matrix equation, so if this is a times xy equals uv, then this has a unique solution for precisely when the determinant is non-zero. And it's given by the following. So essentially, you can think of this inverse as, sort of dividing by A. So really sort of what we're doing here is, if A inverse exists, so if we have, some equation, A xy equals uv, if A inverse exists, then we just sort of multiply A inverse to both sides. We know this gives us the identity, but the identity times anything is just that thing. So we just have xy equals A inverse uv. So let's do another exercise. So do give this a shot. So using the formula, oops. Solve the system 11x minus 5y equals negative 9, negative 4x plus 2y equals 4 by converting it to a matrix equation. Okay, so converting it to a matrix equation, and then just sort of use this formula up here. So just multiply the vector by that. Okay, so give that a shot. And now let's go over the answers. So your matrix equation, you should have gotten 11, -5, -4, 2 times xy equals -9, 4. So we'll call this A, and then we're just going to need to compute A inverse using this formula up here. So we swap 2 and 11, and then we make the -5 and the -4 negative again, so become positive. And then we divide, I should have left more room. We divide by 1 over the determinant. So that is 11 times 2 minus -4 times -5. And I think I forgot to say something about this, but if I write a scalar out in front of a matrix, that just means I multiply. If I just write like a number in front of a matrix, that just means like I multiply everything inside by that number. So this is 1 over 11 times 2 is 22, minus -4 times -5, so that's just positive 20, so we get 1/2. So our A inverse is 2 over 2, so 1, 4 over 2, so 2, 5 halves, and 11 halves. Whoa, 5 halves, not 5 11ths, and 11 halves. So then what we can do is just, solve for x and y by just multiplying this thing by the inverse. And what we should get here is, 1, -9 plus 10, so that should be 1, and -18 should be 4. So x equals 1, y equals 4. And going back, let's just check our work. 11 times 1 is 11, minus 5 times 4 is 20. So 11 minus 20, yep, that's -9. And -4 times 1 plus 2 times 4. So -4 plus 8 is indeed positive 4. So we checked it, the formula works. All right. So I realize video is getting kind of long. I am going to push through, try to make it up for you guys later in the week, but I really sort of want to get back to the fundamental sets of solutions so that we can do this on our worksheet on Tuesday. So okay, now let's return to ODEs. So given two functions, we're going to introduce, so let's say y1 of x and y2 of x. The Wronskian or sometimes called the Wronskian determinant, of the pair y1, y2 is the determinant of y1 of x. So our first column is y1 of x, and then the derivative of that. And the second column is y2, and then the derivative of y2. So just to write it out, y1, I'm not going to write the x's, times y2 prime minus y1 prime times y2. And I should say that we denote this as just w of y1, y2. Or w of y1, y2, and then we might write an x just to emphasize what our variable is. All right. So now we get to sort of the main thing we're sort of building up to. So if y1 and y2 are solutions to a second-order homogeneous linear equation, note, this has to be homogeneous. And the Wronskian of y1 and y2 is not the zero function. So this is sort of clear. This is sort of an important point. It's okay if for some x values, using the formula you have, it's okay if it's zero sometimes. It does actually mean something. It means that some things might go wrong at that particular point. But the main thing we want is for this to just not be zero. Then y1, y2 is a fundamental set of solutions. Or FSS for the equation. So recall what that means is the general solution is y equals c1 y1 plus c2 y2. And just to say real quick about sort of the y is the Wronskian, the thing to check. Well, if the Wronskian is non-zero, then we can always sort of, so we already know that these are solutions, C1, Y1 plus C2, Y2. We talked about that on Friday. If these are solutions, right, it's like, it doesn't matter if you add before or you plug Y1 and Y2 in and add after. You know, like everyone always wants to do with a square root, but you can't. So if that, then the system of equations, you know, C1, let's just say it's non-zero at 0. C1 Y1 prime 0 plus C2 Y2 0 has a solution. So we can solve every single sort of IVP as long as the Wronskian is non-zero. And so like by existence and uniqueness theorem, that means like we have all the solutions. Right? Because like I could always, if I have any solution, I could plug in 0, I could take the derivative, plug in 0, get some answers. But then like that's a solution to the IVP, but then whatever the solution to this is would also be a solution to the same IVP, so the two solutions have to agree. Okay. So I'm going to leave you guys with one exercise. And again, I apologize for the length. I will make it up to you guys by making the later videos in the week a bit shorter. So find the general solution to y double prime plus 5y prime plus 6y equals 0. And here's sort of how you should go about doing it. So for your hint, look for solutions of the form y equals c, or y equals e to the RT. So you should find two of them. So let's say e to the R1, e to the R2, and verify the two of that form. Are a fundamental set of solutions by computing the Wronskian. Okay, so pause, give it a shot. Okay, so let's do it. So if y is e to the RT, then y prime is r e to the RT, and y double prime is r squared e to the RT. So we can plug this in. Y double prime plus 5y prime plus 6y equals 0. R squared e to the RT plus 5r e to the RT plus 6 e to the RT equals 0. We can divide out by e to the RT, and then just have a quadratic r squared plus 5r plus 6 equals 0. That factors as r plus 2 times r plus 3. So we get two solutions. Say y1 is e to the negative 2t, and y2 equals e to the negative 3t. Right, so now we compute the Wronskian. So e to the negative 2 times e to the negative 3 there, and then minus e to the negative 3t, negative 2 e to the negative 2t. So negative 3 e to the negative 5t plus 2 e to the negative 5t. And so we get e to the negative 5t as our solution. This is not equal to 0. So e to the negative 2t, e to the negative 3t is a fundamental set of solutions. And our general solution is c1 e to the negative 2t plus c2 e to the negative 3t. All right, and we will end it there.